All right, folks. I was through the next video to about like 3 minutes left to go in it, and then it just crapped out my phone and said, you don't have any more storage. So I just went through and I deleted a lot of things. I didn't realize how much crap I had on my phone. All right, those games I don't play anymore. All right, so here we go. We're going to the next part. Now, in the last video, we had gone through what the average atomic mass is and whether or not you, what the mole is. And, if you look at the periodic table, we can get the average mass, blah, blah, blah. What a mole is, it's really big. It's like a dozen, but a lot more than that. And when you have something as small as the atom, you need a lot of them. So that's why we need Avogadro's number, Avogadro, that number in order to get any significant mass for something so small. Now what we're going to do is get the mass of anything on the periodic table. And of course, we now know we can get that in two ways. You can get it as AMUs. It's the same number value. So for carbon, it's like 12.0011. Or is it, but the units are different. So is it in AMUs or is it in grams? If you have one atom of carbon, it's 12 AMUs. If you have a mole of carbon, it's 12 grams. Same number, just how we ask the question is going to determine whether or not we use AMUs or grams. Now, there is one thing that I do want to talk about a little bit, and that we're going to, if you look on our list of what to do next, it says molecular mass. Molecular mass. So we're going to calculate the masses of molecules. Molecular mass. Now, typically, molecular mass, sometimes you'll hear this said in a number of ways, and we know that the person saying it, and we know what they mean. And we'll go, okay, that's fine. You did technically, you might not have said it right, but we'll go, okay, I know what you mean. So if I tell my lab partner, could you take this marker and go back and put it on the balance and get the weight of it? Could you go weigh this, please? Technically, that's not right. You're not using a balance to weigh something. You're using it to mass something, but we know what you're talking about. If you tell me to go weigh this on the balance, I know what you mean. I mean, deep inside, I'm probably going, silly, but I know what you mean, okay? When we say molecular mass, that's the way we should say, not molecular weight, although that's done a lot. I mean, chemists will do that. They'll talk about the molecular weight of something, but technically they should be saying molecular mass, but we know what they mean. Also, a molecule is not every compound. Say it this way, not every compound is a molecule. Molecules, and I had mentioned this earlier in the naming part, are two nonmetals. So you can have two nonmetals, that's a molecule. You can have a metal and a nonmetal, that's an ionic compound. So an ionic compound, though, is not a molecule. So we shouldn't technically be saying, let's find the molecular mass of sodium chloride. Because technically sodium chloride is not a molecule because it has a metal and a nonmetal. So we shouldn't say molecular mass. But if you did, we know what you mean, and we're okay with that. So molecular mass, no. Formula mass, yes. Formula unit or formula mass is how you would say it correctly, technically correctly, for something which is an ionic compound. But again, I'm using terminology that we all know what it means. It's just that technically you might be wrong in how you say it, if you mean like the molecular weight of this, not right. Two reasons it's not right. That would be double wrong because it's not a molecule and you're not getting the weight of it. All right, I'm just kind of nitpicking here, but pointing that out that there are words, and words have meanings, but in this case, we can kind of get away with if we don't exactly use the correct words. What we're going to do is use the periodic table to get masses of compounds. So masses of compounds, all right, like what? Like what? Give me an example, all right? Here's an easy one. Start out with this one. H2O, all right? Easy one to start with. So let's get the mass of water. Let's get the mass of it. So what I do is I stay organized, and I call this bookkeeping. Getting masses of things is not difficult, but you can make errors if you're not organized. You don't make sure things are set up correctly. So I always teach my students that do it this way, be organized. Because on an academic adventure coming up very soon, you have a little academic adventure, aka test, and on that you might get a couple of these molecular masses you have to calculate, and they're worth 5 points each. But the answer is worth 1 point, the setup is worth 4 points. And the reason I do that is because if you just give me an answer and it's wrong, I can't give you any points on it. Well, I can't give you any points if it's wrong. If it's right, I can give it to you, but if it's wrong, I can't give you any points because you didn't show me how you got the answer. So show me what you did, and I can pick out, usually pretty quick, the math error you might have made, and I'll take a point off. And if you do the rest of it right, then I can give you 4 to 5 points. So if you don't give me any way to give you partial credit, and partial credit is your friend, trust me on tests, I can't give you partial credit. So make sure you give me a reason to give you partial credit. So show me the setup. Show me the setup and how you did it. Here's what we do. Write down the elements that we have in the compound. Write down how many we have. 2 hydrogens, 1 oxygen. Multiply by the mass off the periodic table. And we're going to round these to whole numbers. Round off hydrogen to a whole number, it's 1. Round off oxygen to a whole number, 16. All right, do the math, multiply. 16 and 2, add them together, boom, we get a mass of 18. 18 what? That's the question you should be asking. 18 what? Remember, we talked about there are 2 ways to express the mass in AMUs or grams. So is this 18 AMUs or is it 18 grams? The answer to that question is, how was the question asked? Were you finding a mole of water? If you were finding moles of water, grams, 18 grams. If you were finding the mass of 1 molecule of water, and water is a molecule, hydrogen, although it's on the left side of the periodic table, it's considered to be a nonmetal. So we're going to, when it comes to naming compounds, remember, we're going to name this, it's water. Remember how to name this? Prefixes, dihydrogen monoxide. Dihydrogen monoxide, ooh, nasty stuff. Don't drink dihydrogen monoxide, it's bad for you. So this molecule, if we had just one of it, would get 18 AMUs, 18 atomic mass units. So just 1 molecule AMUs, a mole. 18 grams. Okay, I think I beat that dead horse enough. I wonder where that saying came from. Beat a dead horse. Who would beat a dead horse? Think about it. What's wrong with you? Okay. Came from somewhere, though. Somebody look that up. Okay, get back to me. Let's try another one. A little harder. Not too hard, though. Let's try calcium sulfide. Okay, this isn't harder at all, is it? Oh, so let's make it a little harder. Let's go calcium sulfate. There we go, calcium sulfate. So write down what we have. Calcium, sulfur, oxygen. Write down how many you have. 1 calcium, 1 sulfur, 4 oxygens. Then go to your periodic table, look up the masses, round up to whole numbers. Calcium is 40. Sulfur is 32, oxygen is 16. Do the math, 40 times 1. Anybody calculator? Anybody? Thank you, Marty. 40. And 32, Marty, thank you. Did you get this one yet? 4 times you got it? 64? Okay. So Marty, very good at that calculator. Add these all up. I got this one, Marty. Relax. You've tough day so far. So 6, 9, 11, 12, 13, so that's 136. That's 96, yeah, 136. 136 what? Exactly. If it's a mole of calcium sulfate, 136 grams. If it's actually technically this is not a molecule, but I'll say it, 1 molecule of it, technically that's wrong, it's 1 formula unit, okay, it's an ionic compound. Then if we had just 1 of these, or just say 1 calcium sulfate, then go to 136 atomic mass units. All right, so that one, 3 a little bit harder. Let's try another one, a little harder. We'll just do 1 more of these. You do the same thing on these all the time. Just be organized and multiply out and add them all up. Let's try 1 more. Let's try this one. Name that bad Larry. Do it. Name it. So if we were to name that bad Larry, then you would immediately recognize that there are 2 polyatomic ions here. Ammonium and phosphate. That's what it's called. It's called ammonium phosphate. They're just the polyatomic ions, so you just name them. Okay. Looks like it might be a little bit more organizing. Now, when we're doing mole, stoichiometry calculations, mole calculations, there are some that would be like this, that I would jot them down because try to do them all in my head. I can do a lot of them in my head, but this one I might make a mistake, so I would be organized. I would write down the masses and go ahead and add them up like we're going to do right now. So what do I have? Nitrogen, hydrogen, phosphorus, and oxygen. All right, how many nitrogens? Be careful. That 3 is a multiplier for everything inside, so 3 nitrogens, 3. 12 hydrogens, 1 phosphorus, 4 oxygens. Oop. Multiply first. Nitrogen is going to be 14. So 3 times 14, yeah, it's 28, 38, 42. 42. Hydrogen is 1, so that's just 12. There's only 1 phosphorus. That rounds to 31. That's 31. And the oxygen is 16, so that's 64. So we go ahead and add that all up. 4, 5, 6, 7, 8, 9. And then 10, 11, 12, 13, 14. So it should be 149, but don't trust me. Don't trust me. Add them all up, see what you get. Let's do it one more time. Whenever I check myself, okay, I usually just throw myself into the board. It's a hockey joke. It's funny. I check myself. Now, I usually will add in a different way. So this time I'm going to go with 64, 65, 75, 85, 95, 105, 107, 108, 109, and 109 plus 4 is 149. Okay, so that's right. So we're now 149 AMU or gram, depending on whether or not we're talking a mole or 1 of it. Okay, that's organization. So if you were doing this on a test and you made a mistake and you multiplied 4 times 16 and got 48, and you got the wrong mass, I can see what you did wrong, you lose a point. If you don't put this down and you give me the wrong, I can't give you any points. So again, please be organized and write down how you're getting your answers so I can give you partial credit. So that's how we get the mass of compounds. Look on the periodic table, round off to a whole number, add them all up, do some bookkeeping, be organized, and how many you have of what element. Do the math right, and you'll be okay. All right, now if you look on here, the next thing it says is percent composition. Percent composition. I'm going to go ahead and leave this up here because I'm going to use it for my percent composition example. But I'm going to do an easy one first. Go back to water. Okay, let's go back to H2O. And we had hydrogen, oxygen, 2 of those, 1 of those, 16, 1, 2, 16, total of 18. Okay, that was our first mass that we calculated for the water. Percent composition is the amount, percentage by mass of each element in the compound. So if we have 2 elements in the compound, okay, we know percent should equal 100, right? You know that. So we know that there is a certain percent of that mass that's due to the hydrogen and a certain percent of the overall mass that's due to the oxygen. So if I have this set up and organized, this makes percent composition easy because I now have an organized setup that shows me that 2 for hydrogen out of the total of 18 is the mass due to the hydrogen. I also now can see that 16 for the oxygen out of a total of 18 is the mass due to the oxygen. I have this set up for percent composition already. This makes it super duper easy to figure out the percent. So remember how you get your percent? How to get any percent. Any percent. Like if you had a test and there was worth 41 total points and you got 37 points out of 41, one, you're going to probably look at that and go pretty happy with that. But I would say, how do you get your percentage? You know, you take 37 divided by 41 and multiply by 100. To get a percent of anything, you always take partial divided by total. partial divided by whole. So that's how we get our percent. Take the partial for the hydrogen 2, that's part of the total, divide it by whole. So we're going to take each one of these masses, 16 and 18, and divide it by 18. All right, 16 and 2 and divide it by 18. So 2 divided by 18 and 16 divided by 18. To get it to percent, you should multiply by 100, because that's going to get me to some decimal form. So to get a percent, you multiply by 100, and you'll have your percentage. That should come out to be 1 of 8, so like 12 and 88, but let's just do it out. So 2 divided by 18 is 11%, 11.1%. So this comes out to be 0.111 multiplied by 100, and we get 11.1% is the percent of the total mass of water due to the mass of the hydrogen. Now, we know these have to equal 100, so you can just take 100 and subtract that and get your percent due to mass, percent of mass due to the oxygen, but we'll just do it out anyways, and hopefully it comes out to be 88.9. All right, let's do it. 16 divided by 18, no, 88.9. Whoa, math works. And of course it's 0.888, blah, 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 so we're going to multiply by 100 to get to percent, and this will come out to be 88.9%. So that is my percent composition. Percent composition is the out of the total mass of the compound, what is the percent of each element's mass in that total mass of the compound. So here, this one's a little bit more complicated. I have 4 elements, each equaling the total mass of 149. So each added up equal total 449. So take each one and divide by 149. Divide 149. Divide 149. I'm doing this sideways, so I don't have a lot of room here. Divide 149. And then multiply by 100 to get a percent, but let's go ahead and do this. And 42 divided by 149, 42 divided by 149 equals 28.2, 28.2%. For the nitrogen, out of the total mass, nitrogen accounts for 28.2% of the mass. 12 divided by 149 goes 8%, or 8.1%. And the phosphorus is only one of them, so 31 divided by 149 is out to be 20.8%. And then last 64. Of course, right now we could take 100 and subtract these and get that value. It's probably just easier to do it though, faster. 64, what do I have there? Divided by 149. And we get 42.95. So I'm going to make that 43. We're going to make that 43%. Now, if we add these up, they should be 100. I mean, of course, there's a little bit of rounding. So it's not going to be exactly 100.0. It should be right around 100, give or take a couple of percent, 1/10 of a percent point. So we do this up. We add these. 43, 53, 63. 63, 71, 81, 99, 100.1. So we get 100.1 if we add those all up. Close enough for government work. That's what I always say. So that is going to give me, if we add these up, we get 100.1. A little bit of rounding there. And so we now have our percent of the mass. So who uses out of the total compound, who is the most massive out of all of them? Now you might say, well, the most massive, I mean, that's phosphorus. Yeah, but there's only one of them. So in terms of the total amount of mass, it's the oxygen that does most of the dirty work there. Even though we have 12 hydrogens, well, they only have a mass of 1. That's the least percent of the mass out of the compound. So that's how we get masses of compounds and how we get what's called your percent composition. Your percent composition, this is important. This stuff comes back to be used in future chemistry in a few weeks and in labs. So please, if you don't just have this go by somewhere in your brain, write down in your head, write it in there, that this is going to come back and I'll need this later on in labs and stuff. Okay, so it's written in there. You're good to go. All right, video over.